So welcome to the webinar. This is a webinar that we organize in the Circwaste project. My name is Joachim from Syke, and it's organized as part of the Palvelukeskus service center in the Circwaste project. And the goal of today's webinar is to give the participants an overview of LCA and carbon footprinting methodology, and especially give an introduction to a tool called CCalc2 that was developed at Manchester University. And for just to give you a very brief reasoning why we are looking now at CCalc, that's a tool that we have identified in the Circwaste project as one of the most suitable tools that could be used by companies, by municipalities, by regions, by pretty much anyone with not any solid knowledge of lifecycle assessment. It's a tool that contains lifecycle inventory data and is free. So that's the reason why we are looking today at this particular tool. For the purposes of the introduction, or the webinar will be hosted by Dr. Harish Jeswani, and Harish is a research fellow at the university at the Sustainable Industrial Systems Group at the University of Manchester in the United Kingdom. And since joining the Sustainable Industrial System Group in 2008, Dr. Harish has worked on various research and consultancy projects on lifecycle assessment and carbon and water footprinting and on corporate sustainability. And he was actually part of the team which developed the CCalc tool. So as such, he has a very deep knowledge of the software, and he obtained his PhD in corporate climate change strategies from the University of Surrey. Now the structure of today's webinar, we have 3 hours booked for this. So first we will get an introduction to lifecycle assessment and carbon footprinting for about an hour. Then about half an hour would be an overview of the tool itself. So Dr. Jeswani will show us the tool and the main features, the main functionalities, and then later on he will continue with a couple of case studies. We took into account your wishes when we send out the questionnaire, and so the case studies should at least partly reflect the most frequently those topics that most frequently popped up from your answers. So without further ado, I would like to welcome Dr. Harish Jeswani, and I will give the floor to him. And before we do that, just I want to remind you that we are recording the webinar for further dissemination, to be viewed by other people who cannot participate today. And if you have any questions, you can either ask straight by unmuting your. No, you cannot, because you are muted by the by the organizers. Otherwise, it would be messy. So just if you have any question, there is a Zoom group chat on the right side of the window, and you can ask there either publicly or privately anything what comes on your mind, and I will go through the questions and ask if on your behalf if there is anything to ask. So let's start.
Good morning. Hi, my name is Harish Jeswani. Thanks, Yakum, for the introduction. Can everybody hear me?
We can hear you well.
All right, okay. So I'll turn off my video and start with the sharing my screen, and then we can go to directly to the webinar. Okay, so this webinar is about an introduction to the concept of carbon footprinting, and in this we will try to cover some basic concepts about life cycle assessment and carbon footprinting, as carbon footprinting is a subset of life cycle assessment. So it's good to look at the broader concept of life cycle assessment. And then we will look at a tool in order to, if we want to model or assess a carbon footprint of a study or a product. And that tool, as Yaku mentioned, it's called CCalc, which was developed at the University of Manchester. And we'll also try to do one or two case studies depending on the time, and to see how those studies can be modeled in that tool. And we will be taking some questions, I think, in between as well. So the presentation as the first part, and then maybe an hour or so, we'll be focusing on the concept of life cycle assessment and carbon footprinting. And in the next part, we will be going more into the tool. Okay, so first we'll start with the concept of life cycle assessment. Traditionally, industrialists, policymakers, government, scientists have been focusing on the reducing pollution from most immediate and visible sources. For example, directly from the industry, in terms of how to reduce air emission, how to reduce the wastewater discharges, also some cleaner production option within the industry. That thinking is called gate to gate. Also, a lot of the time, government require industries to report the emission occurring from their own facilities. But often, most of the emissions or environmental impact occurs beyond the boundary of the plant or factory where the manufacturing occurs. For example, the energy they may be sourcing from a grid or a coal-fired plant, or materials or chemical which can be coming from different countries or sources, transport associated with it, as well as once the product is made, a lot of product can have impact during their use stage. And they will also result in generation of some waste, which will require treatment. So this traditionally was not fully covered in that thinking. That's how the concept of life cycle assessment came into. And it was in early 1990s when people started more focusing on this, that we should look at the more holistic approach from the material where it is like either mined or excavated or cultivated, it's transport related emission within the factory usage, and how it is disposed of, whether it is recycled, reused. So this concept or thinking is called cradle to grave approach, which from the terminology means from the birth of or start of the product till its end of life. Now even we are also talking about more circular economy where the product will be reused and recycled. So that looking into all of those activities of a product is called a life cycle of the life cycle thinking or life cycle. And if we want to do a study or assessment, then it becomes a life cycle assessment. And so as I say, in 1990s, this tool was developed, which is called life cycle assessment. What it involves, it involves basically quantification of our environmental burdens, or when we say burden means whatever emissions or waste or flows which are occurring due to this product or process or even activity, we quantify that from, as we say, cradle to grave, from each stages, and it includes all energy, material used, and waste and wastewater discharges. And once we quantify those burdens, then this tool also helps us how to translate those burdens into environmental impacts. Like you would have heard, like carbon footprint is one of them, which is also global warming potential, acidification, ozone depletion, water footprint. So how do we translate? So this tool allows us, the methodology have been developed to translate those burdens into environmental impacts. One of the main objectives of this tool is to, once we identified or quantified those impacts, it can help us to find the opportunities to reduce those impacts or find the alternatives. So in 2006, the methodology was developed, or standard, this called international standard for ISO 14044, which has standardized how a LCA should be conducted. So it provides a framework in that, like, what are the stages or steps one should follow so that these studies are done in a very standardized way and comparable with others. So it has 4 stages. First is goal and scope definition. Second is inventory analysis. Third, impact assessment. And fourth, which is interpretation. So in goal and scope definition, generally it requires, I'll go a little bit more detail in the following slides. So in goal and scope definition, where it requires that the purpose or aim of the study should be defined, what is included within this study, which is system boundary, is also defined, and what is the unit of analysis or functional unit. Once that goal and scope has been defined, then the next step is the collection of data. So, which is we call inventory analysis. And once we collect the data, we can estimate the burdens, which, like, what are each emission source from that system. And in the next stage, those inventory or raw data is converted into the impacts. And ISO allows what impact categories we can select. So it says, requires that all relevant impact categories should be selected in LCA. Don't have to include everything, but there are more than like 20 type impact categories. And once we select those relevant categories, and then there are various methodologies available to estimate those impacts. And this interpretation stage is a more iterative process within that. So each stage, once we define our goal or functional unit, we can look at the then we can identify what are the significant issues, also from the results and conclusion. And we can always, after from this stage, go back and modify our either aim of the study if we needed to, or our data collection scheme, or if we have missed a particular impact, we can go back. So this study this stage is not a linear, but it's a more iterative process. Now I will go into a little bit more, like providing some examples of our each stages. So in the goal of our scope, so first, like defining what is the purpose of a study. So the purpose could be, we've identified the hotspot. Hotspot here means what are the main contributor or main processes which are contributing to the majority of impacts in that. And once we identify that, then we can focus on reducing from those. We focus our resources on impacts which can have a higher return or reduction potential. Also, we can identify the main impacts, whether it is main impact is carbon footprint or acidification or ozone depletion, for example. And once we have identified the hot spots, we can look for the opportunities or improvements. So far, if it is emissions are occurring because of energy use, then we could look at whether we need to change the source of energy or having more energy efficiency measures or changing in some plant design, for example. And this can help in designing new product or processes, and to compare as well as the alternatives if option A is better than option B or not. The next is the system boundary. Again, I'm going a little bit through those terminology in case if you're not aware, so that when we will be talking in the case study, so bear with me in that. So system boundary in LCA term is what we are going to include in our analysis. So in a cradle to grave approach, as I was showing, it will include everything from the start of which you can be, extraction or mining or cultivation process till the product is finally disposed after its useful life. And any resources used in terms of energy, water, materials are accounted, as well any emission and waste leaving that system. But also in LCA, it is also common that sometimes especially for business purposes, if their product is like an intermediate product and that product is going to another study, they may only focus on the cradle to gate approach, where only they can focus on the extraction till manufacturing of that, and the all immediate steps in the between. And then the next industry, if they want to use this data, can use further, if there is a further processing, and then use recycling, etc. So for every study, it's important that this system boundary should be defined, what has been included. And at the same time, it's also possible that some steps we can decide that because they are either not very relevant or our focus is not on those, we can also specifically mention that these have been excluded. Next is the term in the goal and scope is requirement of the unit of analysis, or functional unit as we call. It basically defines the function of the system, and then it will allow us making comparison on equivalent basis. So generally we could say, take analysis per kilogram of a mass of any product, or if we are looking at energy, then it could be per megajoule basis. But often for complex products, these units may not be not will be a good for comparison on equivalent basis. I just give an example here mentioned is regarding the packaging. So as we know, if we want to have a packaging for say 1 liter of water, if it is in a glass, it will require much higher mass of glass. But if it is a PET or any other material, then because these are lighter materials, the mass is required less. So if we want to compare packaging per kilogram of a packaging material, then it's not a useful comparison. In that sense, we can define our functional unit in terms of a bit differently. We could say store 1 liter of water, and then we calculate the amount of packaging, etc. needed to that. And same that could be applied, for example, for pants. So if we are to compare two pants, one is a say high quality and another is an average quality pant. So high quality pant, then means one option is we compare based on 1 liter, but as we know that 1 liter comparison would be giving us misleading results. So we can, because high quality paint may give us a higher surface area, it could last longer before we need a recoating compared to the average quality. In that sense, we would have to take into account, maybe we want to say, we want functional unit in terms of a surface area over the lifetime. We say, okay, we want a 10 meter square of a wall over the 10 years of time. then we calculate amount of paint required and then assess for each of them and compare them. After defining our system and setting the functional units, the next step, which is one of the most crucial steps in the conducting either LCA or carbon footprint, is called inventory analysis. And it's also more resource and time consuming step, because in this process step, we collect all required data. And if the data are missing, then we would have to make certain assumptions, etc., and we have to, based on our own professional or literature or judgment on those things. So here, as an example, is, let's say, 1 ton of a particular product we are analyzing, and then we have this basic. So these are 4 life cycle stages: extraction and processing, manufacturing, use, and disposal. And here we are just showing some of the, say, emissions here related to greenhouses like carbon dioxide, methane, and nitrogen. So just as so this process, though it would require a lot of other things, I'm just giving as an example. So if we are looking at the only emissions of greenhouse gases, so we collect all emissions, say how much CO2 is generated in extraction, or so methane, or nitrous oxide, etc. And once we have this, we can then, means if you want to call it here, it's called burden of carbon dioxide, where B as a burden. So burden will be collecting on this functional unit basis and adding them up. And so we can add all carbon dioxide flows together, all methanes, and similarly nitrous oxide. So, and there are, as we know from each process, there are so different, many different type of emission would occur. It could be sulfur dioxide, it could be emission of volatile organic compound. At the same time, a lot of input would be required in terms of materials and chemicals. So in the inventory part, we would be collecting all those data for this functional unit. And once we have this data or as an inventory, then the next step would be impact assessment. This is relatively a simpler step, because in that we translate all those burden into impacts. In the simpler one, I say, is because a lot of softwares are available to do that work. All they require from us is to put all the inventory data which we have collected. And once we put into those data into those software or tools, we get normally those results. But these results for those impacts, and these impacts have been, there are methodologies behind that which have been scientifically agreed, that how do we calculate, say, carbon footprint. This follows the IPCC, International Partnership on Climate Change, and then there are also other methods for calculating resource depletion, ozone layer depletion, which follows Montreal Protocol, acidification, and so on. So I'll just to show as an example how we calculate from inventory to impacts. So as we were saying, so once we have an inventory of all, say, greenhouse gas emissions, then basically each emission would have a characterization factor, which we call, which as a factor that's, for example, carbon dioxide causes the impact of carbon dioxide on global warming, or we measure as a 1, but methane in relative terms is 25, and nitrous oxide is 265. So each burden would be multiplied with that factor, and then it's a summation of that. So and that will give us once we have multiplied all burdens with their equivalent characterization factors, we get the net results as a carbon footprint or global warming. Here is a bit more like an example. So in the previous, we at inventory level, we said these are the CO2, methane, nitrous oxide emissions occurring from different stages. And once we summed up, so in terms of, so this total burden of this particular system boundary is, in terms of carbon dioxide, is 4.5 kilogram per ton, methane is say 0.5 kilogram, and nitrous oxide is 0.1 kilogram. And then these will be multiplied by their potency factor or characterization factor, as it's called. So for carbon dioxide, as I was saying, it's 1, for methane it is 25, nitrous oxide 265, and then it gives us the net value. And this often is, we can do in Excel or in on our calculators, but since there will be, under each process there will be so many different emissions occurring, that's why we often use softwares to do those. And there are software, as you may be familiar, there are some are very simple software which easy to use. Then there are others very professional and more comprehensive as well, like software, LCA softwares. And depending on, they give more probably accurate results compared to those simpler ones. And in terms of interpretation, once we have done our analysis, we could see where are the major burdens, what source, what process or stage is contributing to them. And then as a result, we will identify the hotspots, and also we evaluate findings. So interpret why those emissions are occurring, and what is their significance. So that all happens during this stage where you discuss importance of your findings. And also in LCA, as I was saying, sometimes the data are not available as a primary data. So we may have to make certain assumptions. So for example, we may not know exactly type of a truck which is carrying the raw materials. So whether it is a 32-ton truck, or whether it's a 16-ton truck, or whether it's a 7.5. And so we can make an assumption, okay, we selected this particular type of truck. And if during the identification of hotspot, we find, oh, transport is a significant contributor, then we could look at sensitivity analysis. Maybe we want to check our assumption that, okay, because we didn't know what type of vehicle was used, we can change the type of vehicle and see how the results would change. And if we are finding, for example, the results are very sensitive to that assumption, then we could look into finding more, like a little bit investing into more, finding that proper data for that, or correcting that assumption. Also, if we are doing a comparative study, then it will help, we could also decide on the basis of what is the best alternative. And often in LCA, because as we're saying that if we are assessing more than one impact, then it's possible that option A may be better for a particular impact, but option B may be better for the other. And then how do we select the best alternative? That's also in this part, we would then maybe go and discuss which impact is important for why, and then select accordingly. So in terms of LCA has its also limitation and difficulties. One is it's a bit, LCA as a whole is a bit complex, though I have just given a simple, overview of it, but its methodology is complex. It has been between scientists and specialists have been developing. And once we go into more detail, then we find those complexities as well. And then the other is one of the second most important issue is the availability of data and the reliability. It's not about just the primary data, how much material is used or how much energy is used, but it's also about the secondary data, whether that material was produced in a particular country, in a particular factory, for example, or shall we use an average data of the global material production? Same, for example, for energy, electricity, whether that is if a factory is using from a plant which is a renewable source of energy, or we use grid mix, and all those could have a huge implication on the results. So in that way, data availability and the reliability. Also the data, a lot of data, background data are available in various databases or in also different publications. Then sometimes, as you might know, that this carbon footprint ILCA data change over the time, because if, for example, we are moving towards more renewable energy, then all of the background emission would reduce. So the data gets older a bit quickly nowadays. So in terms of, we may have to look whether those data we have got are reliable as well, or in terms of their time, or also in terms of whether they represent the particular production system. The other is, it can be time consuming and resource consuming, depending on how complex is the study which we are conducting. If it's a simpler process, then maybe it's easier to collect those data and put in a simpler tool to calculate. But if we are looking for a more complex product, or even where the data lies with various suppliers, and then collecting from the supplier, so all the supply chain, could be very time consuming process. And also LCA often is done by, would require a bit more specialist knowledge, so that can how to interpret, and then those means with those experience and knowledge, they know which type of data, where to look, as well as how, in terms of more knowledge about the methodology, so that the assumptions can be made accordingly. One of the things with the LCA results is also they can be misinterpreted depending on, because of so much assumption or complexity, and if the system is not defined, or functional unit is not properly defined, then they can be misinterpreted. So that's why we have this standard, and every study should be conducted in that standard. But also, even within the standard, there are still option where people can select the data from different source, etc., and then can get a totally different result. And to avoid that, ISO also requires that if you want to use this study, for example, for marketing purpose or communicating with your customers, then requires that this study needs to be peer reviewed by independent verifier. For example, they can review the methodology use, the data quality, as well as the overall results, and then they give then they will say whether this study has been conducted following that methodology or not. And often industries or businesses which they are using for marketing purposes, they follow this route. I was mentioning about the data sources, the background data. So these are some of the well-known sources. Some are commercial, others are more government sources. So equivalent is a more widely used database source. It is developed in ETH Zurich, and it is a commercial database, and it provides environmental data for over 12,000 background data sources. So ranging from material production, construction material, energy sources, waste disposal, wastewater treatment, transport. And these two, CIMA Pro and ThinkStep, these are companies which have developed LCA tools. They have their also own databases as well. besides in US, there's a US life cycle inventory database, which they have developed for their based on US conditions. European database is also have been done under ILCD for some of these substances, and besides there are French, German databases as well. So that ends basically the overview of the life cycle assessment, and now we will move to the next part, which is on the carbon footprinting. So carbon footprinting, as you know, is all related to the impact on climate change, and as IPCC reports, which have been doing this assessment on the climate change for like past 20 years or so, they have been publishing their annual report every 4 years. And this is this report is developed by various scientists collaborate in that to develop those. And most of the scientists agree that our climate is changing because of greenhouse gas, increase in greenhouse gas emission caused by human sources activities. And also, if we look at the emission trend, it has been increasing since industrial revolution, mainly because we have started using more fossil fuels, also due to other land use and agriculture activities. And this graph shows the data for past 40 years, from 1970 to 2010. And as we can see, the total greenhouse gas emission in 1970 was 27 gigaton per year, and in 2010 they have increased by 80% to 49 gigaton. And in past 10 years, even we have been seeing a lot of like policy development on Kyoto Protocol and now Paris Agreement, etc. But the emissions are still increasing at the like a rate of past 10 years was 2.2% per year. And most, again, in terms of emission, if we look which greenhouse gases are contributing, then these are three main greenhouse gases. One is carbon dioxide, another is methane, third is nitrous oxide. So these three gases account for more than 95% of total greenhouse gases. Carbon dioxide, there are two sources. One is related to fossil fuel combustion or industrial processes such as cement, and that accounts for around 65% currently for total emissions, followed by carbon dioxide, which is occurring from forestry and land use change related activities, which is around 11%. Methane emissions, which largely occur from agriculture related activities from animals and rice cultivation, they account for 16%. Nitrous oxide, again, is also related to agriculture activities because of the use of fertilizer as well as from the manure, which accounts for 6%. So these are the major gases. And besides other like refrigerants and other freon and CFC, those gases have very high impact on climate change, but currently the emissions of those are relatively low compared to the other gases. If we look in terms of economic sectors and their contribution on the graph on the chart on the right hand side, this shows the breakup of in terms of the direct emission from different sectors and indirect emissions. If we look at from the direct emissions perspective, the major contributor is electricity and heat production, which accounts for 25% of global emissions, followed by agriculture and land use change, 24%, and industry directly contributes to 21%, and then transport. this electricity and heat production, they are, because these are generally used by these other sectors, including building and industry. So if we can look at that, electricity indirectly contributes to these emissions are indirectly related to those sectors. So buildings are domestic or commercial building, half of them are related to those, and the other half roughly are related to the industry. So industry is 21% direct, and if we account for heat and electricity, then it could be another 11% emissions. So as we see the various these IPCC reports are saying that greenhouse gas emissions are increasing, and whatever now we do, the climate change is happening, and as a result, we know the temperature is rising, which can have effect on sea level, on weather pattern, and resulting in a drought and floods. So scientists agree that we would have to adapt as well as mitigate. So in terms of adaptation, because some of those impacts are now inevitable because of the past emissions, and we can't, even we stop emitting altogether now, still there will be some of those impacts would still be occurring. So in that sense, we would have to prepare for adaptation, becoming by developing our infrastructure, cities, or our resources more resilient to effects of, say, for example, floods and droughts. But at the same time, if we still continue to emit at the current pattern, then we will be making this adaptation even worse. So in that sense, we would have to focus on reducing those emissions. But for both cases, it's also important that we need to do carbon accounting and management, because once we start measuring, then we know we can manage it, focusing on where are the options and how those can be reduced. And that has led to this concept of carbon footprinting, which is being currently widely adopted by business and industry as well as public sector, that we estimate all greenhouse gas emission related impact from human different activities. This is generally means it's expressed as carbon dioxide equivalent. It could be like in terms of kilogram or tons. And it has been defined as we're saying, there are several greenhouse gases. So each could have a different impact on climate change. And it's called, the effect is measured in terms of a integrated radioactive forcing, how it changes that in the climate. And because some of those gases have some lifetime, some have shorter lifetime in the atmosphere, other has longer. So carbon dioxide, it's believed more than 100 years. Other methane may have a shorter, or nitrous oxide. So they have developed a factor based on that time frame. And so what 1 ton of methane would be equal to carbon dioxide, or 1 ton of nitrous oxide, or CFC. And those factors has been developed by IPCC. And they do update every few years based on their more scientific readings. And we then calculate accordingly. This concept also, carbon footprinting, also is known as global warming potential, and sometimes you may even hear as an impact on climate change, or climate change impact. So what does it include? It would include, as we say, because it follows LCA approach, life cycle assessment approach, it would include all direct as well as indirect emissions. So direct emission means emission occurring directly from the industry or plant, but also indirect emission could be due to electricity usage, due to transport, or from the other supply chain stages, including disposal of waste in landfill or incineration. And also in many cases, the indirect emission could be much more higher. And this probably is more like, for example, if a car factory wants to estimate their emission, the direct emission from their car manufacturing plant would be much lower than, because cars, a lot of those emissions occur during their use stage. And it's not only for those, but there are a lot of other products or processes which we use where the indirect emission would contribute much more. Or for some instance, for example, during use stage, and this is, say, refrigerant we use, the production may not be that carbon intensive, but once we use, there will be leakage, and those refrigerants have higher global warming potential, so they cause higher impacts. And same applies with the other various, including air travel and some even industrial products. As a result, that we should follow life cycle approach to include both direct and indirect emissions from a particular activity or process. So what is life cycle approach? Again, as I'm showing the same diagram, so we would include all cradle to grave approach, which is from the extracting or mining or excavation processes where raw materials are produced, then they are processed into products and following the use, disposal, etc. And all stages which involve like all inputs within in terms of material energy from that system, and we would also consider the all emissions and the waste and how they are treated. In terms of methodology, carbon footprint, as I said, it also follows this life cycle assessment or life cycle thinking in the broader, but so the ISO standard is still valid to conduct LCA study, but subsequently, because this focuses on a particular only one aspect, and there have been further development and to provide more guidance on how to conduct carbon footprinting study and what type of emission should be included, what should not be, etc. So one of them is the ISO standard called 14046. They are more like a reporting what should be reported and how to report. Also, this is a US-based greenhouse gas reporting protocol, which also provides detailed guidance. In addition, there are also mandatory carbon reporting required. For example, under emission trading scheme, various countries have developed their own laws where under, like, for example, in European Union, or they call it scope 1 or scope 2 or scope 3 emission. So some are only, they focus on direct emissions, other include all supply chain emissions as well. In the UK, this standard PAS 2050, British standard PAS 2050 was initially developed to provide more methodological guidance on carbon footprinting. So these are the standards generally followed in conducting carbon footprinting. Now we would look at some examples of the carbon footprint for these major economic sectors: energy, industry, transport, and food. So first, energy sector. Let's take an example of life cycle electricity. Again, we will start, for example, how that fuel is produced, all emissions occurring during the production stage of the fuel, combustion in a power plant, and then any processes occurring in terms of making electricity to a voltage or at a grid level, and then use. So basically, we would, again, in the life cycle, we would look at the emission occurring from all background stages till the emission and waste from each of the life cycle stage. So this is just an example of carbon footprint of different electricity option. So as you know, coal is, we all know that is a highly polluting, it has higher carbon dioxide emission, and we can see its On average, it could have around 900 gram per 1 kilowatt hour. But gas is a relatively cleaner fuel, so it has relatively about half of the impact as from the coal. But then we look at these various renewable sources, they have much more lower impacts, especially hydropower and wind, because these do not involve any combustion. Even in nuclear, the combustion related emissions are not occurring, but in nuclear, we would have some emission occurring during the processing of fuel and its disposal, etc. Compared to these three, the biomass and photovoltaics, these are based on a particular study. The emission can vary a bit from one study to other. So they have photovoltaics have a bit higher than compared to say wind or hydropower. Again, the main reason is the development of the components or production of those components used in the solar energy are require a lot of energy and emit certain gases and has higher. In case of biomass, again, the emission could occur due to use of fertilizer in the cultivation and nitrous oxide emission. Also, if there is a, for example, land use change, and often biomass would require a lot of transport as well, bringing from the field to a power plant. So those can contribute to the emission of carbon footprint or carbon footprint impacts. Next, we could just have some look at the example for transport. Again, life cycle, if we want to assess the carbon footprint of transportation, we would follow the full life cycle from production of fuel, also would include the manufacturing of vehicles in which that would be used, and then the emission occurring during the use phase or during the transport, and also at the end of the life disposal of those vehicles. And this shows some values for the carbon footprint for different options, and these values have been taken from eco-invent database for a particular types of travel. So as you can see, the results here are shown as gram carbon dioxide equivalent per person kilometer. So it's based on the 1 person 1 kilometer impact. So if a person wants to travel, say, for a kilometer, then plane travel has highest, of course, and even within the plane, generally the shorter distance travel have more higher impacts compared to longer distance. There could be two reasons. One is generally for long distance travel, we have a bigger plane which can carry a lot of passengers. Also, the emissions during landing and those and uptake are also then accordingly divided. In terms of surface travel, we look at the rail. Again, long distance has a lower carbon footprint, much lower compared to even bus. And bus, if we are traveling by car, then it's almost double the impact of the traveling by bus. In the transport, a lot of impact is due to fuels, and so those impacts could vary what type of fuel is used. Here we have, I think, assumed the diesel used in those, and probably here either diesel or electric fuel is used. But here in this slide, we can look at the carbon variation in carbon footprint for different fuels. So on the left-hand side, it's showing the fossil fuels, petrol and diesel, which emit around 85 grams CO2 per megajoule. But then the next, we could see there is a reduction if we are using bioethanol or biodiesel. And within bioethanol, it also emission depend upon the feedstock used. Wheat could have relatively lower reduction because, again, it's the cultivation of it, use of fertilizer, etc., could, and further processing causes more impact as well compared to sugar beet, or we are using, say, woody biomass. In terms of biodiesel, some of these feedstocks are, these seeds, the cultivation where it's happening is also causing land use change, where the forests are being, for example, palm oil or soya, in Brazil, palm in Malaysia and Indonesia being cut for the plantation purposes. This also results in this emissions occurring from that stage. But if we compare it with the, say, used carbon oil, which will have a much more used cooking oil here, UCO is used cooking oil, which could reduce the, if it is converted into biodiesel, it could reduce the emission from fossil fuel 70 to 80%. Often carbon footprint gives, as I was saying, only a smaller picture of the impacts. There could be other impacts as well, and it can happen sometime. We are reducing carbon footprint, but we may increase other impacts. This is just as an example, as we are showing that if we look at in the previous example, we saw that wheat can reduce some emission compared to wheat bioethanol compared to petrol on a megajoule basis. But if we look at the other impacts, because wheat cultivation involves the use of fertilizer, which can cause eutrophication because of leachate of nutrients. Also, fertilizer production and application cause acidification impact on the environment. And use of pesticide can cause toxicity related impact. So they can be in some cases even significantly higher compared to the, say, fossil fuels. And in such situations, then we would have to, our policymaker would have to decide which impact is more important, because there will be some trade-offs. We can reduce one impact, but the other impact will be increasing. Are we ready to accept that increase? Next is about the emission from industrial sources. So as at the initial start of the presentation, I was mentioning about the carbon footprint of industry. It's caused by direct emission as well as indirect. Directly, industry contributes 21%. And if we include, say, power, electricity and heat usage, then the total emissions are about 1/3 of all global emissions. And in this pie chart, it shows that the three main contributors industrial sectors are iron and steel, or metallic, ferrous metallics, and then followed by non-metallic minerals, which include cement plants, and then is chemical and petrochemical. And all these three industrial sectors account for 2/3 of the direct emissions within the industrial sector. This slide shows the carbon footprint of some commonly used chemicals. So if we could look at that, carbon footprint impact could vary from 1,000 or 1 ton per ton of the substance to even 9 ton. In the case of, for example, this nitrogen fertilizer, ammonium nitrate, I have about 9 ton per ton of impact. But other basic chemicals, because they require less processing, so the impacts are, lower for ethylene, propylene, or acid, hydrochloric acid. But as we move further, where the more processing is required, for example, from ethylene to propylene, we are starting developing more polymers like PVC, HDP, is polyvinyl chloride, high density polyethylene, or polypropylene. And because of additional processing, use of energy, electricity, etc., the carbon footprint increases accordingly. And for polystyrene is even higher. In the chemical sector, most of the emissions are related to the production of the chemical because of the processing stage involved. But also there is partly occurring because of the base material, which is either extracted in the form of crude oil or gas, which is used as a feedstock. Also, those chemicals, once we dispose it, can cause impact during the disposal and use. Use stage is more common to some chemicals such as CFCs or refrigerants, where during the use they will be released into environment, have higher impact. In disposal, the impact can occur if we are some of those chemicals, once we incinerate, either to produce energy or just incineration to dispose it off, those emissions would occur during those stages. Now we'll talk a little bit about the agriculture and food sector. So in terms of agriculture sector, direct emission, majority of emissions are coming from the fertilizer in form of nitrous oxide, followed by methane emission occurring from the cows and sheep, and then some also from their manure. Besides, other agricultural activities can release those same gases. Also, rice is also as a particular crop, because rice cultivation, the way it is cultivated in most of the countries, during cultivation it also emits a lot of methane. So it is one of the major direct contributor to greenhouse gas emissions. If we want to assess a carbon footprint of a food product, then we would start from the cultivation, processing, storage at the retail. Often processed food product would require some sort of refrigeration, and that could have a higher impact. And then a lot of food either is could be end up as a waste, either whether it's unedible part or even sometimes in parts we have a waste as it because we overbuy them or it's not suitable. It ends up often in landfills, and those emissions would occur from landfills. And this slide shows a comparison of carbon footprint for some day-to-day food items, and shows a bit comparison between meat versus vegetables. As we can see, beef and lamb are at the highest end with the carbon footprint impact of around 14.3 kilograms, largely because of the methane emission from enteric fermentation, but also because of they require a lot of food to grow it. Compared to pork and chicken, because they do not have enteric emissions, and so they have about 1/3 of the emission compared to beef and lamb. But if we look at the vegetables, they are much lower emission occurring from their cultivation or production. However, for vegetables, it varies depending on the cultivation method and where it is being cultivated. For example, this is just as an example. If tomatoes grown in Spain in a open field in the summer, then they have carbon footprint of around 0.3 kilogram per kilogram. But if we compare it with the tomatoes grown in greenhouses in winter in Netherlands and UK, where they will require a lot of energy to maintain the temperature, then the emission could be an order of magnitude or even more higher than those. So a study done in UK by DEFRA in the UK, they found that if the tomatoes grown in a greenhouse, which is being operated by either coal or natural gas, then it could even have impact as 9 kilogram per kilogram. It's just not the cultivation stage contributes. Sometimes the other life cycle stages would contribute in the carbon footprint. Here, just to give us an example, how the carbon footprint would vary between how it is stored at a retail or a use stage. For example, if we are juice, which is consumed sold as a fresh juice in a refrigerator, then it could have about 60% higher carbon footprint compared to juice which is in a Tetra Pak and stored at an ambient temperature. This is a lot related to the use of energy in refrigeration, and also it's besides the retail stage, the other stage could also influence is the type of packaging also in the various food products. So generally, cartoon and PE has lower impacts compared to, say, plastics. For example, here it shows PET compared to glass. One of the reasons for glass, the higher impact, as I was previously mentioning, because we require large mass of glass compared to other packaging materials. Also, glass production is more energy intensive. Here, in the skin here shows different options in terms of what happens to the glass, at the end of life. If it is recycled, then the impact are lower. But if it is made from virgin glass and only dispose of a landfill directly, then it could have a higher impact. So it's also means depending on the type of material as well as depending upon how it is made, whether it is made of recycled content or how it is disposed as well, whether it is reused or recycled or landfill, could influence the overall impact. So one of the use of carbon footprinting at a consumer level has been for carbon labeling here in UK and also in some other countries, where we see for some products, some retailers or manufacturers have used this as to communicate with their consumer how good their products are, and that will provide some information about the overall impact of their product. So that ends the session on the overview of life cycle assessment and carbon footprinting. And I think we can have some questions if we have any. Hello.
Thank you for the introduction or for this lecture. It was very interesting. At the moment, it seems that there are no questions in the chat, but if anyone wants to ask a question, then please write it in the chat, and then Harish can read it from there. And otherwise, I think that we can take a few minutes break, and then we would continue with the introduction to the tool.
The Circwaste project receives support from the LIFE program of the European Commission for the production of its materials. The views reflected within the content are entirely the project's own.